that we will just recapitulate that, and then again we'll do the next one. So all of you, have the calculator ready, because all these examples will be for all the topics. There will be an associated numerical, and in fact, I'm trying to make the class more like a tutorial so that you work out here only. Uh, so this was the question we discussed, that there were two star connected loads. We know what is the meaning of load now. And for this curriculum, we are only considering balanced loads. That means in the star connection, the three phases, the impedances are all equal. So this is how the two loads are. The first load is having Z1 as in each of the phases, and the second one is having Z2 in each of the phases. The values of Z1 and Z2 are told, and what is in addition given is also, obviously, you have to give the phase sequence. Okay, so by this time we understand what is the meaning of this sequence, and as soon as you are told the sequence, you can mathematically represent what it means. So, so what is also given is the line voltage. The line voltage VAB is given 500 volts, that is the RMS value. So you can quickly represent the line voltage. So let us assume that the line voltage is along the reference. Okay, so the line voltage is assumed to be reference. So then the job is to find out the different currents in the loads, and ultimately what is the line current. So by the current in the loads, what we mean, what first we have to find out what is the current in each of the phases of the load, and then how they combine to generate the line current. So this is the okay. So once the line voltage is given and phase sequence is given, we know how to write down the voltages, and the phase voltage. Okay, since this is star connection, the phase voltage is 1 by √3 times the line voltage, which we already know. So since we have given the line voltage along the reference, the phase voltage, that is VAN, will be lagging the line voltage by 30 degree. Okay, so this is the VAN, the location of VAN. And so obviously it is little bit shorter than this, because it is 1 by √3 times. The magnitude wise also it is less. So I've kept it shorter. So once we write down VAN, you can also represent the other phase voltages. Now this phase voltage VAN will result in the phase currents in the two loads. Okay, here I have just shown the phase currents in the A phase. Okay, for the first load it is the I1, for the second load it is the I2. So we can write down what is the value of this I1 and I2. So I1 is VAN by the impedance, which is Z1, and you know how to do it. You know the Z1 value is given, VAN is there. You can you get I1. Okay, so I1 is say 7 minus J2, so it will result in basically a current that will what, lead or lag the phase voltage. 7 minus J2.
Lead the voltage.
It will lead the voltage. So it will be more towards the positive side. So the voltage VAN was minus 30. This ultimately results in minus 14 degree. Similarly, I2. So this is I1, and similarly I2 we can find out VAN by Z2. Now this is Z2 is 4 plus J2, so that will result in a current that is lagging the phase voltage. Okay, so this is becomes 64.54 minus 56 degree, and this is somewhere here, and this is somewhere here. So this I1 and I2, combined will generate the line current IA. Okay, so IA is equal to I1 plus I2. So you know what is the how this addition has to be done. That is by completing the parallelogram and then joining the diagonal. So ultimately, it will be a complex number with some magnitude and angle, and that is somewhere between 14 degree and 56 degree. That is at minus 40 degree. So the circuit is a little bit, the phasor diagram becomes a little bit clumsy, but anyway, it has to be done. The angles have to be found out correctly, and then the power factor of a circuit is the angle between the voltage and the corresponding current. So in this case, it will be the angle between the A phase voltage versus the angle versus the A phase current. So cos of the angle between VAN and IAN, and this will result in, so VAN is basically at minus 30 degree. VAN is minus 30 degree and IAN is at minus 40.7 degrees. So minus 30 minus of minus 40 and then cos. So that is basically the power factor, which is the lag, because IA is lagging VAN. And the total power is nothing but 3 times the per phase power. So PP is the per phase power. So if you find the per phase power multiplied by 3, since this is a balanced load, you get the total power consumed by the load. So in this case, what is the power by the word power? What that we mean is basically the active power. Okay. I mean, in most of the times we just speak active power. So if we just tell power, it basically means active power. So the formula is what? 3 into per phase. Per phase means this is the per phase voltage. VAN by 500 by root 3 into the per phase current, that is 97.5. So this IA and into the 0.98. So this will give you the total power consumed by this load, by these two loads. Okay, here we have two loads, 1 and 2. So this is the problem we did in the previous class. So today we will do another new problem. Okay, so this was all about star load. If the loads are star connected, if the impedances are connected in the form of star, so we'll do a next is if the impedances are in delta. So this is basically the generator. Okay, this is basically the generator, a 3-phase generator, where the 3 phases are given, and obviously it is ABC. Okay, by the angle you can see that the angle, phase A voltage is along the reference, then the phase B voltage is minus 120 degree lagging, and then the phase C voltage is at plus 120 degree, that means minus 240 degree lagging. So that is the phase sequence is ABC. And so this is the Y connected generator or star connected generator. Similarly, so if we know all these things, that is the phase voltages, and not just that, it is the magnitudes are same. So this is basically a balanced star connected generator, and we know these phase angles. Okay, so this is the voltages are all same. So this is basically the balanced generator. Similarly, if we draw the line voltages, we know how to draw the line voltages, and they are again all same, because it is the phase voltages are same, so the line voltages are also same. Okay, and the relation is VL is equal to root 3 V phase. The line voltage magnitude, the magnitude of the line voltage is root 3 times the phase voltage, because it is the star connected or Y connected generator. Now this generator is basically, so this is basically the line voltage that is available between A to B or B to C or C to A. The magnitude is always root 3 times the phase voltage. Now this is, and we also know this angle, that is the VAB, it is at a root 3 VPH at an angle 30 degree. Now this is connected to a delta connected load. So this shows the delta connected load. That means 3 impedances ZP. That means the real part as well as the imaginary parts are the same. The balanced delta connected load in the form of a delta is represented like this. So this is basically the delta connected load, and it is connected to the star connected generator. Okay, so balanced delta connected load is connected to a star connected generator through what? What is this medium? Between the load and the generator, what is that?
Cables.
Transmission lines.
Transmission lines. Yes.
Transmission
So
lines.
yeah, so I have joined the generator with the load by a transmission line. Here it is shown within one, it is held within the slide. But this transmission line ideally are, transmission lines are, hundreds of kilometers. They can be 500 kilometer, 1000 kilometer long transmission lines. So one generator is connected.
Sir,
change this delta into star? Means the delta, sir,
Yes.
वो जो sir, that impedance is there, no? Can we change it into star?
Yes, you can change it. You can change it if once if it helps helps you in solving the circuit, you can do it. But obviously, you'll have to apply the formula correctly, and there should not be any mistake. You all know the delta to star conversion formula is already done. The same thing gets applied here. So this is connected to the transmitter. So what we have a very simple case. One star connected generator connected to one delta connected load to the transmission lines. And for the time being, we are assuming as if the transmission lines are having zero impedance. But in ideal case, they will, but in practical case, they will also have impedance, they will have resistance, they will have inductance. Since these are actually wires. So we can, but for the time being, we are considering that they are having zero impedance. Now, as soon as you connect this, then there will be line current going to the phase A, which is IAA. That is the line current from the generator, A phase of the generator to the A phase of the load. Similarly, IBB will be the line current from the B phase of the generator to the B phase of the load. And similarly, ICC, the line current going from the C phase of generator to the C phase of the load. Now, as soon as you connect these, as soon as these currents go, inside the delta, what will happen is there will be phase currents. So for the load, these are the phases. AB is one phase, BC is another phase, CA is another phase. AB is one phase, BC is another phase, CA is another phase. So there will be the phase currents inside the generator, inside the load, where this IAB is the current in the between A and B in the delta connected load, and this IAB is nothing but is equal to VAB by ZP. Okay, VAB, that potential between A and B divided by ZP. All of you are convinced about this? IAB is equal to
Yes.
VAB by
Yes, sir.
ZP. ZP
Yes,
is
sir.
the impedance of the phase. Okay, so you already have VAB at an angle 30 degree. So VAB by ZP. So ZP will have some impedance. Okay, and so that impedance, so that will result in some. If it is assumed to be an inductive in nature, it will lead to a current IAB which is lagging VAB. Okay, so it will be somewhere here, depending upon the value of ZP. Similarly, you will get IBC. IBC is nothing but VBC by ZP. And considering a balanced load and a balanced generator, I have considered a balanced generator and a balanced load. Okay, so again it will generate IBC, which will actually be IAB rotated by 120 degree. Okay, it will be AB rotated by 120 degree. Okay, so it will be IAB rotated by 120 degree. So IBC equal to VBC by ZP. So it is lagging VBC by certain angle which is contributed by ZP. Similarly, you can there will be ICA. There will be ICA, which is again VCA by ZP. Again, it is IBC rotated by 120 degree is ICA. So these are the phase currents inside the delta connected load, and then since we are considering a balanced load supplied by a balanced generator, the magnitudes of these individual phase currents of the load are all same. Okay, because we have considered a balanced situation. So you see these I phase, that is the phase current of the delta connected load, are all equal. So IAB, IBC and ICA are the phase currents of the delta connected load. Now the job is what is basically the line current. That is what is the current drawn by the from the Y connected generator. So what will you do to get the line currents?
Sir, it will be IAA equals
we
to
will add
IAB
the current
minus IC.
IAB plus
Yes, sir.
So we'll have to, at each of these nodes, basically you can apply
KCL.
KCL.
Not an, yes, sir.
Okay.
Yes, sir.
So IAA That is the current going in. Suppose we are applying KCL at the node A. IA is the current going in plus ICA minus IAB equal to 0. Okay, so you will get this is IA equal to IAB minus ICA. Okay, so the line current IA is equal to IAB minus ICA. So you know how to do this, subtraction. So this is basically IAB plus of minus ICA. So plus of minus ICA means you have to reverse ICA. Okay, and then add it along with IAB. So where will be the new current IAB? IA, where will it be?
30 degree behind AB.
30 degree. How do you know? 30 degree.
Because sir, IAB, IBC and IC are all inclined at 120 degree. That is why. So it will be similar expression.
Okay. 30 degree. But okay, that is correct. But what I am asking is, it will be in somewhere in the fourth quadrant. Okay. But depending upon again the value of theta. So it will be somewhere here. Okay, so it will be obviously greater in magnitude than the individual phase currents. The magnitude wise, it will be greater than how much will it be? Root 3 times. Okay,
root 3 times IAB.
So this is the case now. So in a delta connected load, the line current is actually root 3 times the phase current. In a delta connected load, the line current is root 3 times the phase current. Okay, so these IA, IB, IBB and ICA, so you can basically complete this. Okay. They will again be, shifted from each other by 120 degree. And since we have all assumed, the balanced situation, generator is balanced and the load is balanced, they all are equal to each other. The magnitudes of these line currents are equal to each other. And the line current is equal to basically root 3 times the phase current for a delta connected load. Okay. Any question on this?
Sir, I have one question. Sir, like in the previous star connected load, we were adding the impedances of the transmission line directly to the load, like impedances. So what will we do here if the transmission line has some impedance?
You tell what to do.
Maybe we shall convert it into star and then add.
Yes. If you convert, you balance delta, you can convert to a star, and then you can absorb the line impedances along with that phase impedance to get the to do the calculation. Okay.
Okay, sir, got it.
So in the books you will actually find a lot of such numericals, and you should practice all those. But this thing has to be clear that for a delta connection, that is a delta connected load, the line current is root 3 times the phase current. And in the phases, the whole line voltage gets applied. Okay, in the phases A, B, B, C or CA, the individual phases of the delta, the whole line voltages gets applied. Okay. So let us do some numerical on this. If it is okay, we'll proceed with the numerical.
Okay, sir.
Yes, sir.
Yes, sir.
Just a simple numerical. I would want all of you to do that. There is a delta connected load at a power factor 0.8 lag. Okay. The line voltage given is 300 volts. I have not mentioned anything. That means it is RMS. And it actually consumes the three-phase load. That is, the delta connected three-phase load consumes 1200 watts. The question is find the per phase impedance.
Sir, where is the power? Oh, sorry, sir, I didn't notice.
Hmm?
So I
What?
thought
Huh?
I thought the 1200 watt wasn't given. I didn't see that below.
minus
Sorry,
37
sir.
degree angle.
Huh?
60 ohm minus 37 degree.
60 ohm. 60 ohms, sir.
Minus 37 degree angle.
Ohm. Just it is a pure resistance.
No, sir, the impedance value.
No, sir.
Hmm,
And
then
angle minus
degree.
37 degree.
60 minus 37.
36.87.
So the per phase power, there are three phases. Delta connected load. So in each phase, the per phase
400.
power is 1200 by 3.
Yes, sir.
So this is equal to, so since it is delta connected, the entire line voltage gets applied across it. Okay, the entire line voltage gets applied across it. So that 300 volts into we don't know the current. So into the per phase current into the power factor. So from here you will get the phase current as how much? How much is the phase current?
Five
Huh?
5 by
5 by 3. 5 by 3.
1.8.
5 by
1.67.
67.
1.67.
1.6. Yes,
So,
sir.
so this is
Yes,
this
sir,
is the
yes.
current. Okay, so once you get the current, you can find out the absolute value of the impedance. So what you know is the voltage across the phase. It is delta connected, and you also know the phase current. Okay, so you can find out the absolute value of the impedance, which is 300 by I phase. And so this is equal to, so this is the absolute value of the impedance across the load. Okay, so the impedance is basically 180 degree cos inverse of 0.8.
Yes, sir.
Yes, sir.
Okay,
Yes, sir.
so
Sir,
this,
I phase comes 5
huh?
ampere. Sir, I phase is 5 ampere. I phase.
No,
5
no,
ampere.
no. No.
No,
1.65
sir, it is
by
5
3.
by 3.
No, it
You
is correct,
missed,
sir.
you
5 by
missed
3.
division by 3.
That will be 1.6.
You
Yes,
didn't
sir.
divide by 3.
Yeah, you have to be very careful, but because it is not so difficult also, whether you will divide by 3 or root 3, whether you are supposed to divide or not, but you have to be very careful. See, what I have done is I have done the calculation phase wise. I have total power, so per phase power is divided by 3, and then the entire line voltage gets applied because it is a delta connection. So it is 300 into I phase into the power factor. So VI cos phi. And then we got the current, and then we found out the magnitude of the impedance, and this is the actual impedance. Okay, so this magnitude angle form. So then you can represent it in the R plus JX form also. Okay, so this is simple problem. Let us do some complicated problem where so these are these things you can do. Now let us do this. There are two delta connected loads are connected in parallel. Just in our earlier example, we had two star connected loads, but since we have now discussed about the delta, I thought let us give a numerical where there are two delta connected loads in parallel. Okay. All of you understand the meaning of this diagram? Just like the earlier problem where there was star connection, now there are two delta connected loads in parallel. Now what is given is the loads are described. That is the load 1. So wherever there is the subscript 1 is basically the load 1, that is the first delta. It is described by this 40 kVA at 0.8 lag. That is the load 1. So it is 40 kVA at 0.8 lag. So and the load 2 is 24 kilowatt at 0.9 lead. You are given VAB, that is the line to line voltage, that is the line voltage VAB is 440 at an angle 30 degree. So here we have given the line to line voltage which is 440 at an angle 30 degree volts. The question is find the line current. That means the line current, that is IA, IB, IC, and also the total power. Which one is easier to find in this problem?
Total powers.
Power, because I have given the load in the I have described the load with respect to power. Okay, and since this is three phase, power is given by what? Or three phase or in the alternating system, power is given in which form? If you remember the power triangle, S equal to P plus JQ.
P plus.
So there is one real power and there is one
So
real
active
power
and reactive power.
and there is one reactive power.
Yes,
Okay.
sir.
Yes, what less?
For load 1 it is reactive.
It is complex power form.
So complex power form. So you have to basically represent both the loads in the complex power form. S1 equal to P1 plus JQ, Q1. S2 equal to P2 plus JQ2. And then you can find the total power. Because both of them are supplied by the same supply. So total power supplied by the supply. So for the first load, what is P? So these are the phase. As soon as I give you the one line voltage, you can draw the other line voltages. Now the question is for the first load, what is P?
So 24 into sine inverse 0.8. Sine
20?
of
32 kilowatts.
So 32 plus J24.
So 32.
32.
So the power
P would be
real power is
32.
32 kilowatts. 32 kilowatts. The P value.
So it is S cos theta. Okay, I have given
Yes,
you
sir.
the S. I have given
Yes,
you
sir,
the
yes.
S and I have given you the cos theta, that is 0.8. So S cos theta is basically the P. And S sin theta is basically the Q. Okay. And this is lagging. So what will be the sign between them?
So the 40 kVA is the magnitude given.
Magnitude given. So how it is related to the real power and active power, and that the reactive power.
So the final answer will be 40 minus 24J. 32 minus 24J.
32 minus 24J. Why?
So it
So
will be
this-
plus, no? In lag the angle is positive. And the phi is
Acha.
positive.
Yes.
So you see in the delta, so many currents will be flowing. Okay, in the delta, and the one answer is find the line current, that is IA. So you have learned how to find out the line current for a delta if there is a single delta, but I have given you two deltas. And I have given you two loads described in different form. One is a lagging load, the other is a leading load. The power factor is different. Okay, so first find out the total power, because first you have to represent the load in the proper form, in the P plus JQ form. I have the form I have given for load 1 is different from how the load 2 is described. Okay, in the load 2 I have given you the P and I have given you the power factor. Okay, so I have given you the P, so you have to basically find out Q. And there is a power factor leading, so you have to decide what will be the sign. But in the load 1, what I have given is root over of p square plus q square. I have given you root over p square plus q square, and I have given you the power factor. So what is S1 equal to? That is load 1.
Sir, 32 plus 24
32
J.
plus 24J.
Yeah, so you have to find out. I am showing the steps. So 32 means with 40 into cos theta. 40 into cos theta plus 40 into sine of cos inverse 8. Okay. So plus 40 into sine of cos inverse of 0.8.
Yes, sir.
Okay, so you have to note down the steps, but it's not very difficult, because once you know the different, the mathematics we already done, and then you are all experts in sine theta, cos theta. Okay. And we have just considered the power triangle. Okay, I have given you the P, that is P and Q. P and Q are the two powers, active power and reactive power, and S is basically the diagonal. So in the first load is described by what is given is the S and the power factor angle. So from that you can find out. Oh, sorry, what is missing? Can anybody find my mistake?
J ta nahi.
Sorry. You all give the J. Anyway, let me correct it. Otherwise, I will miss later.
కరెంట్ పోయింది మీ సైడ్కి పల్లె కరెంట్ పోతుంది రోజు మనకు పోవట్లేదా రోజుకి ఒకసారి పోతుంది నిన్న పోయిందా పోయింది మొన్న పోయింది ఈరోజు పోయిందా పోయింది ఎప్పుడు పడుకున్నప్పుడు పోయింది మళ్ళీ వచ్చి
Can you see my screen?
No, sir.
No, sir, not yet.
No, the sharing has gone. Okay,
No,
I'll
sir.
share it. Now can you see?
Yes, sir.
Yes.
Yes, sir.
Yes, sir.
Okay.
క్లాస్ వినకుండా డాన్స్ వేస్తున్నావా
Some background noises.
Background noise, all of you, it is your responsibility to unmute individually. I am telling you, otherwise I will mute all. And then I will not know whether you are understanding or not. So this is the S equal to PS1 equal to P1 plus JQ1. And these are the steps to find out how to find out the P1 and Q1. So this is equal to 32 plus J24 kVA. Okay, so if you take 32 square plus 24 square and square root, you will get that 40. That is given to you. Similarly, find out S2. Because this is the second load, but it is given in the form of P and the power factor.
So
P is directly
24 minus
so P is directly given.
24
Okay.
minus 11.62.
Yes,
So P
11.624 J.
So P is directly given. So what is the kVA? So
80
P
by
equal
3.
to P equal to
240 by 9.
P equal to S cos theta. Okay. So it is basically 24 by 0.9.
Yes, sir.
24 once you do 24 by 0.9, you basically get the kVA, and then you have to find out the sine of which
minus
sine of
So we
cos
have
inverse sine of
Cos inverse 0.9.
cos inverse of 0.9. But since this is a leading load, okay, since this is a leading load, so there will be a minus sign.
Yes. So we could have directly used tan instead of doing all this.
You can do anything.
can we
but
not use tan?
Sir, no, sir. Somebody said yes. I wanted to say if I could use tan.
No, if it is trigonometrically correct, you can do many other things, but just the Q will be unique. Okay, so my steps are okay?
Sir.
So
Sir, S1, sir,
kV. So this whole, so kVA is our non-reactive power, na?
kVA is what?
So reactive power.
Reactive power kVA.
No, that's the apparent power. That's the apparent power.
It is the apparent
It
power.
is volt ampere. It's the apparent power.
Okay. I'm just multiplying volt and ampere. Okay, but what is the reactive power? Somebody was asking.
VAR.
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 Volt ampere reactor.
Yeah. So what will be S2 now? S2.
So 24 minus
Will be
11.6242.
So you see that because it is leading, the minus automatically comes. So it is
Yes,
24 minus J 11.62 kVA. So once we have this S1 and S2, then your actually second part of the problem is done. Because the second part of the problem is 20 total power. So you just add these two, you get the total power. Okay, so the real part gets added, the imaginary part gets added. So overall, what is it? Effectively, it is what type of power? The two loads together effectively is what? What type? Leading or lagging?
So lagging.
Lagging.
Lagging. Okay, because it is plus 24 minus 11. Okay, so it will be the two loads together. That means the supply, that is the source, will basically provide lagging power to the two loads, though one of them is leading. So effectively it is lagging. So right, so the first part of the question is find the line current. Okay, to find the line current, you actually need to find the phase currents. Okay, the phase current, and I have given you two deltas, and in the earlier example I did one delta. So basically you have to apply the same methods, but for the two delta, and then do the apply the KCL. So IAB is IAB1. So this is the delta connected load. Okay, so what is the voltage getting applied across the phase? What is the voltage getting applied?
VAB.
40.
The line voltage gets applied. The entire line voltage gets applied because it is the delta connected load. So IAB is basically equal to
VAB upon Z1.
VAP upon Z1, but here we are only given the power.
Yes.
Yes, sir.
Okay, so it is 32,000 divided with, so 32 kVA. So the active power is 32 kilowatts. So 32 kilowatts is in the three phases. So per phase it is 32,000 by 3. And the line voltage that is applied is 440 into 0.8. Okay.
Yes,
that is the line current, magnitude of the phase current in the fast load. Okay, so P is equal to VI cos theta. P equal to the real part of the power. So from that, because in this question only the power is given. Okay, so to find the current you have to use basically the power. Because you are asked to find the line current. So now, so what we are doing is we are finding the phase currents of the first load. So IAB1 equal to 32,000 by 3 divided by 440 into 0.8. And where will AB1 be?
Sir, I have a doubt, sir. VAB is not given RMS, sir. It is absolute.
VAB, if nothing is told, it is RMS.
Okay, sir.
RMS value is noted like this.
Okay, so where will be the location of the IAB1 phasor? Because ultimately we are.
It is lagging. It will lag.
It is
below,
lagging whom?
It's below the reference line minus 30.86. 87
It is lagging whom? Do you lag
Voltage.
So it will lag.
It should be minus 6. 87
So,
from the
so
reference.
IAB1, the magnitude is 30.3, and the angle is, that is already 30 degree minus the angle
Cos inverse
divided by 0.8.
Yes.
Okay.
30 minus 36.7.
So this basically results in 30.3.
Minus 36.86.
Yeah, so
Yes,
it
sir,
becomes.
yes, about it.
So all over minus 6.87 degree.
Yes, sir.
Sir,
So you know
I have a
the,
question. Sir, like in this question, see, we have found the entire like complex power, right? Total power. So if we forget we ever had two loads, and we consider one load only, and for that we consider that power, and then directly use the relation for active power, won't it be correct? Then we can find that phase current in that what do you call it, that source, sorry, that load, and then we can multiply it by root 3 to find the line current. It should be same because we are
Yeah,
considering
you check it.
equivalent load.
You check it. Check it. It should be working. Okay, you check it. Well, a numerical can be done in many ways. You later on do it and find out. In that case, you will directly find out the currents. So here
Yes.
I am going to find out individual currents and do the KCL, but you check it by other methods, and if that is efficient, you can also do that. So this is IAB1. Then you can complete the other currents in the first load, which will be all 180 degree, 120 degree away. So this is how we get the current of the first load, IAB1, which is basically minus 6.7 degree with respect to the reference. But as Om has asked, but if the question specifically has several subparts and asks you draw the individual load currents, then you have to basically do it separately.
Yes, sir. Then we have to do it separately.
Okay. So since this is a balanced load, I am just focusing on only one current in one load, and the other currents you can basically draw by rotating that by 120 degree. Now, what is IAB2? Similarly, you can do IAB2, and there the active power is 24 kilowatts. So it is again the per phase power is 24,000 by 3 divided by 440, but the power factor is different, 0.9.
20.2 angle 55.84.
Okay, so this is the magnitude, and so the IAB2 is 28.2, that is the magnitude, and at an angle 30, but this is a leading power factor. So where will IAB2 be?
Plus cos inverse 0.9.
It will lead PAV. Okay, it will lead, so it will be plus cos inverse of 0.09. From here
55.84.
So from here you can find out the angle of IAB2, and then you have to draw the phasor. So it is 55.86 degree from the reference, and IAB2 is somewhere here. So magnitude is 20, so I have drawn it a little bit shorter than IAB1. And once you have IAB2, you can draw the other phasors. You can draw IBC2, ICA2. You can draw the other phasors IBC2 and ICA2. And then what is the task? What is the task?
Vectorially adding IAB1 and AB2 to get IAA.
So the task is to find out the line current.
IA1 plus IA2.
So the task is to find out line current. So applying KCL at A. A means by A, what I mean is A1 and A2 are combined. If the transmission line impedance is 0, so basically it is the same point. So Applying KCL, what you get? IAA, that is the incoming current,
Is equals to IAA1 plus
plus
IAA2 minus
ICA1.
ICA1 minus ICA2.
Okay, so you can apply the KCL, and this is equal to 0. And IA is equal to this. So find out the value of IA.
$43.44 angle 17.53 degree.
43.
$75.24.
Angle?
Angle
47.53. 47.53.
So you have to carefully do all these calculations. Now you see a lot of calculations are coming, and your accuracy will matter. If you don't do accurately, equations may be correct, then your final answer may be wrong. So you don't get full credit. And you have to basically find out correctly the magnitude as well as the angle.
Sir, 75.25 angle minus 12.46 degree.
75.25.
Yes, angle minus 12.46.
Angle 17.53 I'm getting.
Angle 47.53 I'm getting.
Check, I am getting this. Okay. So, in which quadrant is this angle?
Fourth
quadrant.
Fourth quadrant, sir. Fourth quadrant.
So it is at an angle of minus 12.4 degree and somewhere in the fourth quadrant.
Sir?
And one.
So can we do line current equals to root 3 times phase current?
There are two phases. Which one will you do?
The root 3 IAB1 plus IAB2.
I? But there is ICA1 also, ICA2 also.
Then we have to change the phase accordingly. Means only the magnitudes cannot be added directly.
Okay. So once you have IAA, then you can find out, IBB, ICC also. You can, just because of, it will become clumsy. I did not show it in this phasor diagram, but IABB, ICC is also, since both of the loads are balanced, they are there. But 120 degree shifted, so you can find out the the angles of IBB and ICC also. And the total power that we did initially, which is basically equal to S1 plus S2. S1 plus S2 was already there. The total power is, the real part gets added, so it is basically 56 plus J 12.38 kVA.
Sir, I have a doubt. Sir, why are we representing angles as negative even though we are showing the quadrant correctly?
Angles representing negative means if they are negative, you have to show
Means
it
we
negative.
can only show the magnitude and we are showing the quadrant. So
Yes, sir.
what is the use of the sign?
Yes, sir, yes,
Because
sir.
in two-phase AC we were not showing the sign, and in three-phase we are doing so.
That means you don't want to show the minus 12. You have to just show 12.
Yes, sir. In the phasor
Because we
diagram.
are showing
When we present
yes,
fourth
sir.
quadrant, it is already minus, sir. It is understood that it is minus when we represent in fourth quadrant.
No, but if you don't do it, and then so that angle is reused for some other calculation, and if you put positive, you will get wrong.
Sir, when we will show arrow, then negative is not required. Sir has not shown arrow, no, clockwise or anti-clockwise. So negative should be written.
Yes, that's right. If we are measuring it in anti-clockwise direction, then we have to write that negative one only. I mean, from the reference line.
Okay.
Yes, sir.
Okay, so these are actually very standard problems. Like, so what I've done is I thought that I will do this because in three phase we did star connected load, single load, and then I showed with two loads. And now I did one example where it is a delta connected load, single load we did, and then with two loads. And if you see the books, there will be problems where it is a mixture of loads also. Okay, one load may be star connected, one load may be delta connected, and then you are asked to find out the line quantities and power and all those things. So you have to very carefully do it, handle it by by a similar approach, but very much you have to be alert about the the phasors and what is going on, and all the angles has to be done correctly. So there can be problems where it is a mixture of load. There are multiple loads. Some are star connected, some are delta connected, and when you have asked to find out the line current. And that is the case actually in most in practice that is happening. So there are different types of loads. Star connected, delta connected, all are connected together to the same line, and all of them contribute basically to the line current. So that has to be very carefully determined. Okay. So if it is okay, then we go to another new thing. Any problem about this? Any question on this problem?
Sir?
How
can we quickly calculate ICA1, ICA2 if we know that value of IAB1? Because the magnitudes will be same.
Yeah, so you have to just find the angle by shifting by 120 degree.
Yes, sir. Yes, sir, you are right. Okay, sir.
Okay. So the next thing is the power calculation in a balanced three-phase load. And we just now did the numericals where the load could be star connected and the load could be delta connected. Suppose you have a delta connected load, we just did this. Okay, delta connected load, and obviously this word balanced is required. When I was making this slide, some Professor Das, who is taking tutorial in I think section 10, the word balanced was not there. I was showing him the slides, and then as he mentioned, I introduced this word balance. So in this curriculum, we are only concerned with the balanced load. Okay, so power calculation in balanced three-phase load. So by this time you all know what is the meaning of balanced. So I've given ZP, ZP in all the three phases, and it is a delta connected load. So in a delta connected load, what happens is the entire line voltage gets applied across the phases. So you see that VAB gets applied across phase AB. Similarly, VBC gets applied across BC, and similarly VCA also gets applied across the phase C of the load.
Sir, can you show previous slide? 1 second. Okay, sir. Thank you.
Okay, so these are the line voltages, and so as soon as there is the line voltages applied, their line currents start flowing, and then there are the phase currents in the individual loads. This we already saw. We have done numericals. We have done more than one numerical. Now, and we all know this relation. For the delta connected load, the line voltage, entire line voltage gets applied across the phase. So line voltage equal to the phase voltage, and the line current is equal to √3 times the phase current. And we just now saw, the line current is found out by phasor addition of the two phase currents, and magnitude wise it will become √3 times more than the phase current. So the total active power consumed by this load, by the delta connected load, is how much? Is equal to 3 times the per phase power. The total active power drawn by this load is 3 times the per phase power. That is PP stands for per phase power. Okay, so in this case, total active power means we are considered the total active power of the 3-phase load. Now, 3 is into per phase power.
Can you please once explain why is VL equal to VP?
Who is asking?
Sir,
Tanmay, VL equal to VP, you should be able to visualize. Say VL, this is AB, VAB, this entire voltage is getting applied to capital AB, which is the phase. The line voltage, that is V small AB, gets applied across.
Sir, here VP is voltage across ZP. Sir, VP is voltage across ZP. Okay.
ZP, that is per phase.
So VL is the voltage across each ZP.
VL is the line voltage, that is the coming from the lines, coming from the supply. That is small a. Small a stands, small alphabet stands for the line quantity.
And VP was the voltage of each phase line. So, so then there was the √3 term there. Why is it not here?
No, why was it there? Whatever is the line voltage.
For star.
That was for
because
star.
there was a load.
In load, the line and phase voltage are same per phase voltage.
So we are not considering the generator phase voltage is here.
No, generator is there. Without the generator, there cannot be load. So from the generator, these small a, small b, small c terminals are coming out. And this is the line voltage that is available to be applied across the load. So this line voltage magnitude is equal to the phase voltage magnitude for the delta connected load.
Oh, okay, sir.
So the voltage sources are also in star connection. That's why this is happening.
We are not bothered about how the voltage sources are here now. Okay, so there is a generator from which AB and small a, small b, small c terminals are coming out. Okay, VAB is the line
voltage. My question is that suppose the generator is in star phase, star connected, then in that case the line voltage will be equal to the voltage difference between the two phases of the generator. In that case, it should be VL is equal to √3 VP, and in this
no.
case,
So that is the √3 VP of the per phase voltage of the generator. Okay, but that L which is generated by the generator is now going to the load.
So then, what is the VP in here?
This is the load phase voltage. Well, I have only shown the load here.
Oh, okay, sir. Then got it.
I have not shown see my title of the slide, power calculation balance 3-phase load.
Yes, sir. Got it.
Okay, so the total active power is 3 into VP into IP into the cos phi. So this VP is here equal to how much? VP is equal to, what is the meaning of VP? I am not talking of VP of the Gymkhana, okay. Some of you know the VP of the Gymkhana?
Yes, sir.
Some of you
Yes, sir. Got it.
Okay, there will be some VP, but maybe somebody
Sir, how to become?
So that's to become one.
So there are ways to become. Once you come inside the campus, you have to you have to basically,
Sir, no,
So can we not become from now here?
no, you have to stand in the election. Okay, there will be an elaborate election where you have to. So you have
In
to.
third year, no?
So you have to gather your alliances. Okay, you have to gather your alliances. There are real alliances here. Okay, so okay, I'm not talking of that VP. So it is 3 into VP into IP into cos phi, and so this VP here is equal to the same as VL, but IP is equal to IL by root 3, and your cos phi is cos phi. So the expression becomes the total active power is equal to root 3 VL IL cos phi. Okay, so the total active power. So if you have the measurements of the line, that if the line voltages are measured and the line currents are also measured, and the power factor angle is known, that is the total active power is root 3 VL IL cos phi. Okay, so this is the formula of the total active power for in 3-phase. And so this is the formula for, we have just considered a delta connected load. Now suppose your load is star connected. See, the load is star connected. So this is your line voltage that is coming from the generator. I am not showing the generator. Again, this is VAB and VBC. Again, the line voltages and CA are also there. And similarly, the line currents are also flowing. But in this case, the load is star connected. So across, there is a phase voltage also across the loads. VAN. Now this VAN, this phase voltage is actually 1 by root 3 times the line voltage. Because it is a star connected generator, you see that VAB gets applied across the phase A and the phase B of the load. Okay. So in this case, what you get is VL is equal to root 3 VP. The line voltage that is coming from the generator and getting applied on the load is equal to root 3 times the phase voltage of the per phase. And similarly, IL, that is the load current that is coming.
So because of the new neutral point here, we have the phase voltage and line voltage is different than in the previous case of the delta connection with it was being same. That is what caused the confusion.
No, that is not the confusion. Okay, the confusion is, I understand, because you are confusing with the load and the generator. Okay, but here exclusively you considered the load, and all this addition is basically phasor addition. So this VAB, the line voltage that is getting added, if you break the components, which is VAN and VBN, okay, so then they will be 1 by root 3 times in magnitude.
Yes, sir, got it. Because in the previous case of the delta connection, the VP was the voltage across each ZP, and VL was the voltage supplied between A and B and B and C and so on. And here they are being different. So I got
they are different, and the components have to be found out by resolving into the vectors.
Yes, sir.
And so you see the line current that is going IL is directly entering the phase because it is star connection. So the line current is equal to the phase current. IA is directly entering the A phase, IBB is entering the B phase, ICC is entering the C phase. So line current and phase current are same. Now if you compute the total active power, which is P into per phase power, P equal to 3 into per phase power. So 3 into VP into IP into the cos phi. Now VP is equal to what? VL by root 3. VL by root 3. IP is equal to IL and cos phi. So here also you see the formula comes out to be root 3 VL IL cos phi. So irrespective of the nature of the load, whether it is star connected or delta connected, if your line quantities are given, if your line voltage and line currents are given, and if you know the power factor of the load, obviously it is a balanced load, then the total power is root 3 VL IL cos phi. You don't need to find out the phase quantities if you know the line quantity. Okay.
Sir, I have one question. Sir, will the phi depend on if both are ZP, will the phi depend on the type of the load, star or delta?
No, phi is determined by ZP.
Okay.
R plus Jx.
Yes,
R
that's what I
plus
meant.
R plus Jx gives you the phi. Tan inverse of x by r.
Yes, sir.
Okay, so that is, and it's, for that reason I am repeatedly using the word balanced. Okay, so because in the phases there is the same impedance. Okay. Okay, if this is done, then we'll go to the next thing. Achha, this Saturday there will be the quiz. Okay, I am just announcing this Saturday there will be the quiz. Quiz 3.
And
okay.
sir, homework also.
No, homework is not on Sunday. Sunday because some student told, so we have actually removed all the tests from Sunday. So this Saturday will be the quiz and next Saturday will be the homework.
Sir, tomorrow we will have
Thank
class.
you, sir.
Huh?
Tomorrow we will have class.
Tomorrow is national holiday. If you want, I can take class.
No, sir. I have.
No, sir.
No, sir, we do not want. We are comfortable.
Sir, we already have workshops.
Sir,
Sir, can you tutorial?
sir, today you will finish the 3 pages, sir.
Hopefully, yeah.
Okay, sir.
This is-
So
this is a break-
so the
इसलिए break मत
syllabus
दो, हाँ,
for
हाँ.
so the syllabus for the quiz 3 is 3 pages.
So the syllabus for quiz 3 is 3 page AC, but the tutorial we will do on the 2nd February. Okay.
Okay,
And,
sir.
and 6th February will be the homework.
So can you please send the tutorial sheet?
Huh?
Can you please send the tutorial
Yes,
sheet?
the tutorial and
The tutorial sheet will be on the tutorial. You practice these 3 phases from any other book, any other place you can practice. You can even get the whole tutorial sheets online or something. You will get it.
Sir, could you share the slides, sir, today?
Slides I will share. Okay.
Okay, sir.
Slides because hopefully if I finish it. Okay.
Sir, I have one question.
Mm.
Sir, our like tests and homeworks will be 1 week apart, right? Quizzes and homeworks.
Mm.
So in the homework, will that week's content will also be included, or it will be just that like what we have done in the quiz?
Yeah, but because the third homework will be basically on 3 phase.
Okay.
Module C, this third module, this C module. Okay.
Okay, sir.
But we have removed it from Sunday and did it in the next Saturday. Okay.
Thank you, sir.
Okay, so
Thank you,
now
sir. Thank you, sir.
now we will have to measure.
Sir, excuse me. Sir, in
Thank
the
you,
ET lab, we have been told to do experiments on transformer and all. And sir, in the last week, when we were not taught the 3-phase generator, then we were told to do 3-phase. We are being taught, and sir, in a span of just 1.5 and 2 hours, we were taught everything. And I mean, we didn't understand anything. And when we asked professor, he said that
And sir, they are also
we have
taking
to do
Viva.
everything on theory class. Yes, sir,
No,
they're
no,
taking Viva on top of that.
No,
Grading us every
those things happen when you are here offline also. So for those topics, you have to do a little bit of advanced reading that we can't help, because but anyway we will cover transformer also. But those things happen when you are here, when the students are here to do the actual lab also. But in the online mode, you have to also. I think that is happening. So you have to practice that, by studying from some source. Okay, so the next thing is how to measure the power, and the one vital equipment on in AC circuit is basically the watt meter. It is used for measuring power, and you must have already, as somebody told about the lab, you must have done the virtual labs. That virtual labs, if you do, it is actually
Yes, sir. This experiment we did for our batch, it was the 3-phase.
Yeah, so this
But
virtual
with
labs,
unbalanced as well as balanced.
So virtual labs, that lab is actually developed under my guidance. If you do from that vlabs.itkgp.
So we didn't do this experiment.
We are using MATLAB and Simulink and SimScape.
I know, but if you see the virtual labs, blabs.itkgp.ac.in, that is still better.
Yes, sir. It is also present on there.
But MATLAB takes a lot of time to open on my
Yes,
computer.
yes. Well, I don't know why they are
Excuse me,
suggesting MATLAB, but
Tanmay, did you do this experiment? We didn't do this experiment.
We can
anyway,
No,
so
no,
no
three
discussion
phase.
on the lab now, please. No discussion on
we
the
can
lab
use
now. I just
the MATLAB.
Yeah, I just want to focus on the theory. So the instrument for measuring power is basically the wattmeter, and as you know, power is related to both current and the voltage. Okay, so if you have a load, so the load is drawing a current, and the voltage across the load is also matters when you have to measure power. So wattmeter is an instrument that is connected in, there are two coils. One is added in series with the load and one is added in parallel with the load. The coil in series with the load is basically called the current coil. The one that is parallel with the load is known as the voltage coil. So you see here the short form abbreviation we have given. CC is basically the current coil and VC is the voltage coil. And that is how the two coils are connected. And these are the terminal names. Okay, the current coil, the two ends are called the ML, and across the voltage coil, this is the common terminal between the current coil and the voltage coil. So this is COM, and this is the V that is connected across the load. So one coil carries the current across, that is passes through the load, and the other one is carrying the voltage.
Sir, what does COM mean?
Common.
Okay.
Okay. So now this current coil, since it is in series with the resistance.
Excuse me, sir, what you said? COM.
Common.
What you said is okay.
Common. So see, the current coil is in series with the load. Okay, so it should not have a resistance that will change the load current. So it has to be made with the coil which is low in resistance. Similarly, the voltage coil which is in parallel with the load, okay, it should not carry more current. So it is basically made high resistance. So how do you achieve low resistance? How do you achieve low resistance?
Applying
resistor
in parallel.
What will be the characteristic
Reducing inductance.
It will be a very
reducing inductance.
Low resistance. R is equal to rho L by A. So how will you get low resistance?
Low resistivity.
Okay, resistivity is suppose fixed. Okay.
Area.
By shunting.
Area and length has to be changed accordingly.
Parallel with the area. What said?
So you have to basically increase the area. Okay. So denominator if you increase, so increasing the area means thick coil. Thick cross-sectional area. So what will happen? It will become very heavy. Okay. So that is the current coil. So it is basically thicker. Similarly, the voltage coil should have high resistance because it should not allow current through it. It is in parallel, okay? Because we are only interested, all the load current should go to the load. So voltage coil should have high resistance. So rho L by A. So high resistance you can make by making A smaller. So that is basically thinner.
Yes.
Okay, so compared to the current coil, the current coil is thicker, voltage coil is thinner. So which will actually result in the current coil becoming heavy and the voltage coil becoming light. Okay, these are some of the practical issues. If somebody is designing a wattmeter, they will actually end up with this. Okay, the current coil will be heavy and the voltage coil will be light. And ultimately, there will be a pointer to show the value of the what it is flowing. Okay, so that pointer, will be mounted on. So which coil will be moving out of this? Or which one will be easier to move?
Voltage coil.
Voltage coil will be easier to move. Okay, so it is basically lighter. So the pointer will be on the voltage coil. Okay, so suppose there is a wattmeter in a three-phase system. That means we have a three-phase system. We are considering a balanced three-phase star-connected load, and suppose we are putting for three phases we want to measure the power in all the three phases. So we employ 3 wattmeters. We put for measuring the power in the 3 phases we employ 3 wattmeters. So what we have to do next? We have to basically connect them. So we connect the 3 phases to the 3 wattmeters. So what we have done, all the current coils go to the individual phases. The current coils are connected to the individual phases because the current coil should carry the current. Now what to do with the voltage coil? From each of the wattmeters, there is a voltage coil which is available. Okay, so let us tie the voltage coils together. Let us tie the voltage coils together. Okay, let us tie the voltage coils together, and to keep it some value, some name as X. So this is the situation that we are trying to measure the power in a 3-phase circuit, and for the time being we have considered a star connected load, and that there are 3 wattmeters. Each of the current coils are directly connected to the phases, but the voltage coils are available, and so they are made common. So the power measured by wattmeter A is basically VAX, the voltage coil current in this PA, basically the potential of A with respect to X, current IA dt. So this is the power formula, the average power formula we did earlier. Okay, this formula is okay?
Yes, sir.
Okay, similarly,
Yes,
we can get the expression for power in the phase B, in the wattmeter B is 1 by T VBX IBB dt. Similarly, for the
Sir,
power
what is
in
Px?
Huh?
Oh, okay. X is that point.
X is that point. So voltage at B with respect to X.
Yes, I got it.
Okay, so this is basically going into the wattmeter. And what is VAX? VAX, if you consider, is equal to VAN plus VNX. VAX, similarly VBX, VCX also you can write down. So what is the total power? Is equal to the sum of the powers in the 3 wattmeters. The total power consumed in this 3-phase load, star connected load, is basically PA plus PB plus PC. PA plus PB plus PC. Okay, can you see?
Yes, sir.
Sir,
how is the current through PA is IAA?
Just follow the circuit. IA, PA means this is the current coil. The current coil is carrying IA.
Yes, sir. Okay, got it.
So if you put that expression, so it is 1 by T integral 0 to T VAX IX plus VBX IBB plus VCX ICC dt, which is equal to, so if you substitute this, you can separate them out in this form. So you see there are 2 integrals. On the right side is VAN IAA, VBN IBB, VCN ICC dt. And on then there is a second integral which is VNX IAA plus IBB ICC. So what is the sum of the 3 line currents?
0.
0, sir.
Okay. So what actually remains
0,
is
sir.
basically
Zero.
this. So what basically remains is this. Okay. VAN IAA plus VBN IBB plus VCN ICC integral 0 to T dt 1 by T, that is the average power. Obviously, for this is the second integral vanishes. Okay, so you see in this arrangement, what you have to do? You have to basically buy 3 wattmeters. Each wattmeter is expensive, and you have to buy basically 3 wattmeters. Now, if you make the, so here the reference was basically X, and this is the expression of the power. See, if you make the second phase, one of the phases as the reference, basically you can get rid of 1 wattmeter. Okay, if you make the one of the phases as the reference, you can reduce the price of 1 wattmeter, because ultimately what will matter is whenever you set up some experimental arrangement, the price of the components will matter. So you can basically get rid of 1 wattmeter by considering that one of the phases as the reference. Okay. Okay, can you hear me?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So then we have this new. Okay, so I'm showing a new circuit.
Sir, can you please go to previous slide 1? Yes, sir. Done. Fine. Thank you.
So we have another arrangement now. So there is again a 3-phase load, and 3-phase load, a delta connected load. It could be star connected also, but for the time being we have to delta connected load. So as soon as it is supplied to the 3 phases A, B, and C, obviously this line currents start flowing, and you all know these phase currents will also be there. Now, what we intend to do is to measure the power, and as I told that we need to optimize the cost. So we put 1 wattmeter in the A phase and another wattmeter in the C phase. Okay, and the voltage coils are connected to the B phase. So we have put 1 wattmeter, that is the P1, in the A phase. The current coil of wattmeter 1 carries the A phase current. The current coil of wattmeter 2 carries the C phase current, and the potential coils are both connected to the B phase. Okay?
Sir?
Hmm.
Sir, I have a doubt. Can you go to the last slide once? Sir, so here you said if we make the reference as one of the lines, then we can reduce 1 wattmeter. So here exactly, like if we do that, won't the power?
No, I am not. I am not reducing one of the lines. I'm not reducing one of the. You cannot remove the B phase.
Reducing wattmeter, right? A wattmeter.
I am changing the reference.
Yeah.
I'm changing the reference.
So
and all the phases are coupled. A cannot be independent. B cannot be independent. They are all with respect to each other. You will understand this in the next slide actually.
Okay, sir.
So you see, this is a 3-phase load, delta connected load, and what I have done is I have connected the first wattmeter into the A phase. The first wattmeter carries the A phase line current. The second wattmeter carries the C phase line current, and the voltage coil of the two are connected at the B phase. So you see the first wattmeter. What is the current in the first wattmeter? What is the current in P1? IA. And what is the voltage across the first wattmeter?
VAB.
Sir,
VAB.
VAB.
VAB. Similarly, in the second wattmeter, what is the current?
ICC.
ICC.
And the voltage?
VBC.
IBC.
VCB.
VBC.
VCB.
Yes, sir. CB, right.
Yes, sir.
Okay.
VCB.
So now what will be required? Basically, what will be required is the phasor diagram, because here everything is phasor. As soon as you tell IA, ICC and all, this is AC. ICC will have a particular, suppose the first wattmeter, IA will have certain orientation. IAB will have a certain orientation, and what will also matter is, since it is power, the angle between IA and IAB. Cos of the angle between IA and AB will be required for P1. Similarly for P2. Okay? Power is equal to VI cos of the angle between voltage and current. So for the first wattmeter, the current is IA, the voltage is VAB. So let us construct the phasor diagram. All of you know the phasor diagram of this. VAN is along the reference, then VAB, VBC. And then these are the line quantities. Okay. And this line quantity is VAB. So at a particular angle theta, the IAB is there. IAB lacks VAB but a particular angle theta. IAB, that is this, in the delta connected load, IAB, the current from the current in the phase between the phase current, that is IAB, lacks VAB by at an angle theta in the delta connected load. Okay?
Yes, sir.
Across AB, it is VAB, and IAB lacks that VAB by an angle theta, as shown in the phasor diagram.
Yes, sir.
Okay. So you can find out IBC, IC. So IBC will also lag VBC by an angle theta. Similarly, ICA will also lag angle VCA by an angle theta. Okay.
Yes, sir.
Look at
Sir,
the load.
here we are considering that current is lagging, but it can also lead.
It can also lead.
Okay, sir.
We have for uniformity, we will be basically doing the derivation with respect to lag, and if it is lead, all these changes you can do the changes.
Okay, sir.
Okay, or you can actually draw the phasor diagram and find out what will happen. In fact, there are numericals where it will be like that also. So you see in this load, IAB lags VAB by angle theta. And since it is balanced load, so everywhere it will be like that. IBC will lag VBC, ICA will lag VCA, and so on, all by angle theta. Now, what we are concerned is basically the line current IA. So IA is what? You have already done. IAB minus ICA. IAB minus ICA. So it will be IAB is here. So you have to basically reverse ICA, and it will be somewhere here. Okay, so IA is also somewhere here, and it will lag by an angle theta. It will lag the VAN by the reference by an angle theta. So similarly, you can find out IBB and ICC. So ICC will lag VCN by an angle theta. Okay, so this is the phasor diagram from already we have done earlier. So now we are interested to find the power. Say P1. P1 is equal to what?
IAA VAB.
Yes, sir. IAA VAB.
Through P1, the voltage is basically
Sir, phase difference between IAB and VAB is theta and also VAN and IAA.
Sir is not audible.
Yes,
I
sir.
can't.
No problem.
Yes, sir. Is not
Sir, you
audible.
You are not audible.
yeah. Can you hear now?
Yes,
Yes,
sir.
sir.
Yes, sir. Yes, sir.
So can you see the slide? Hello.
Yes, sir.
Yes, sir.
Yes, sir.
So
Yes,
P1
sir.
is so
Sir,
what?
Sir, the
So what?
angle between IAB and VAB is same as the angle between VAN and IAA.
Hello, sir.
Sir, you are not. Sir, you are not
No,
audible.
not same. Yes, sir. You are not audible.
Connection issue in Kharagpur.
Hello.
Yes, sir.
Now
you
you
Yes,
are
sir.
audible.
Now audible.
Somebody was asking any question?
Yes, sir. The theta between IAB and VAB is same as VAN and IAA.
Yes. Because it's a balanced load.
Okay, sir. Okay,
Sir, how are you writing the power equation? I'm not able to understand.
Power equation is equal to, we are always measuring power across a load. And,
Yes, sir.
So in AC we have seen that the power is equal to the voltage across the load, the current across the load, and cos of the angle between.
Sir, but how are you saying that the voltage across the current coil in P1 is equal to VAB? How are you saying that?
So this is the VAB, the voltage between A and B.
It is not connected in exactly in parallel, right? It is not connected in parallel.
It is not, ideally it is, suppose that the current coil has zero resistance or zero impedance, so then that is the approximation. So across the load, the voltage coil is connected.
Then so we have the load also connected across that wattmeter.
So that load only we are trying to find out, na? That is the voltage.
I'm saying that across the current coil, we can measure here is that the current is IAA, but we cannot say for sure that the voltage is VAB.
Assuming zero loss in the current coil. Assuming very negligible voltage drop in the current coil. As I am telling you, in an ideal situation, the current coil should have negligible voltage drop.
Okay.
The current coil, as I told, is made of thick wire. The rho L by A is more. So assuming it to have negligible drop there in the current coil. Yeah.
Okay.
Sir?
Sir, here you have taken B as a reference point. Then how you have written, sir, VAN?
Which one? I have not written VAN. Where I have written?
VAN, sir. Reference voltage VAN you have written.
Which one?
So in the phasor diagram.
Sir, small VAN. Sir, small AN. Sir.
So that is coming from the that is the AN of the of that one. You know what?
Sir, here you have taken V as a reference point.
No, see, VAB is available. VAN is coming from where? The generator. I have not shown the generator here. So there is a generator that generates all these voltages.
Sir?
Where is the end point, sir?
Huh?
In the diagram not shown.
There is the left side of the diagram is not there. No? In the left side there is a generator there, star connected generator. This small a, small b, small c are basically the line that is available from the generator.
Okay, sir.
Okay, so
sir, we are calculating P1 as the power across AB, point capital A, capital B.
Yes.
So, sir, we should be writing VAB multiplied by IAB. So, why are we writing IAA?
Because the current coil is carrying IA. Current coil is carrying. So this is the wattmeter I have placed here. In the wattmeter, there is two coils. Current coil. In the current coil, the current is IA, and in the
the voltage is VAB across the wattmeter, and the current is IA. That's
IA. Okay.
But sir, current IA is divided into I capital AC and I capital AB. So P1 is not. So P1 should be VA. Power across the ZP resistor should be VAB I capital AB. So why is that wrong?
No, I am not telling the power across the ZP resistor because this is a three-phase load. We are our intention is to measure the total power in the load by using these two wattmeters.
So we are calculating through the wattmeter.
So this wattmeter, we will also be doing experiment. The wattmeter, this wattmeter will have some reading. The second wattmeter will have another reading. So the sum of these two readings is the total power consumed by the load. You will actually do experiments there.
Okay, sir.
Okay, so one we are.
Sir, individual readings, what do they represent then?
They represent one wattmeter reading. The second one is represent another wattmeter reading. Both together is the combined power consumed by the load.
Sir, what means we have 3 ZP and we have 2 readings. So, will it exactly be same in case of balanced load?
Yes. Because this is only possible for balanced load. Okay, this is only possible for balanced load because we are not neglecting the third phase. The third phase we have considered as the reference. Okay, we have put 2 wattmeters, the 2 current coils in one phase, in 2 phases, and the third phase we have considered as the reference for the other 2. So, what is the angle between VAB and IA? Because cos of that angle is there. What is the angle?
30 plus
30 plus
theta plus 30
30 plus theta. So P1 is becoming equal. So that is P1. Similarly, P2 is equal to what? VCB, ICC, cos of angle VCB and ICC. That is the reading by the second wattmeter P2. VCB, CC, ICC, because in the second wattmeter you see carries the current ICC. The current coil of the second wattmeter carries the current ICC, and the voltage coil, across the voltage coil what appears is VCB. So the power measured by this wattmeter is VCB, ICC, cos of angle between VCB and ICC.
Sir, I did not understand how you have told that angle between voltage and current is 30 plus theta.
You see the phasor diagram?
Sir, that
Our
should
co-
be
our
V
co-
small. Sir, that is V small AB.
This small AB and capital AB are, capital AB are same if this line resistance is negligible. This is small AB.
Okay, sir.
If the wattmeter has negligible drop.
Here V capital AB and V small AB is same, isn't it, sir? Okay, sir.
So the angle you get from the phasor diagram. So this AB is what? The line voltage AB. Similarly, CB is the line voltage. And what we have written here is the absolute value. Okay, so P1 is equal to VL IL cos theta plus 30 degree. Theta plus 30 degree plus theta. What is the angle between VCB, CB and ICC?
240 degree.
VCB and ICC. VBC is here. VBC is here. VCB, what is the angle for VCB? For VCB, what is the angle?
So 240 minus theta.
VCB.
Yes, sir, 240 minus theta. 240 minus.
No, I am just asking what is VCB angle?
The VCB angle
90 degree
plus
minus
90 degree. Yes.
VCB angle is 90 degree. Okay. VCB angle is 90 degree. And what is the angle of ICC? ICC का angle क्या है?
120 minus 150.
120?
120 minus theta.
120 minus theta.
120 minus theta. So what is the angle between VCB and ICC?
120 minus theta minus 90. 30 minus
theta.
So 90 minus 120 minus theta. Okay. So this is the situation. Okay. So this comes to VL cos 30 minus theta. Okay. So, okay. So
yes,
this,
sir. Yes, sir.
So
yes,
you
sir.
know, so these P1 and P2 will be the readings. These are the meter readings. P1 and P2. That the two wattmeters are basically measuring P1 and P2, the values. So if you do P1 by P2, you get this. So suppose you have a 3-phase load.
Yes, sir.
And you have connected this wattmeter. You will basically do experiments in the lab. You know, you have a 3-phase power measurement experiment. Okay, so you have connected in the form of a delta or star the 3-phase load, and then you have put connected the wattmeters. That wattmeter terminals M, L, V that you will learn here, and you know how to connect this. This is the connection. You can do it in the virtual lab experiment also. In that only there is a small, there is a coding bug there. You know, the load is purely resistive. Reactive part is having a problem there. So we could not rectify it because of this pandemic, but it works for resistive load. There is a coding error in the reactive part. So if you do P1 by P2, you get cos theta plus 30 and divided by cos 30 minus theta. So from here you can do all these trigonometric manipulations and you can find out tan theta equal to this. Root 3 P2 minus P1 by P1 plus P2. So what is theta? Theta, what is theta?
Angle between VAB and IAB.
Theta is basically the power factor angle. Okay, the theta occurs in the circuit because of ZP only. The ZP The impedance causes the theta. In AC circuit, the
Sir,
theta
actually, it
is,
should be the
right.
reactance. It is what causes the theta.
That impedance causes the theta. Okay, R plus JX.
Yes.
The impedance, because of the you know the nature of the impedance causes theta. So if you do a 3-phase balanced load, in the lab you can do this, and then if you measure this power, then from here by this formula you can find out the power factor angle of the load, 3-phase balanced load. Now suppose if for some situation you are getting this P1 is equal to P2. P1 equal to P2. What does it mean?
So theta will be 0.
Power factor 1.
Theta equal to 0 means what?
Power factor 1, yes. Purely resistive.
Purely resistive. So P1 equal to
no reactive component.
theta equal to rho. So it is theta equal to, it implies pure resistor and power factor 1, which is called unity power factor. So purely resistive circuit is also called unity power factor circuit. Okay. The purely resistive circuit is the power factor is unity, which is 1. So similarly, if your P1 is greater than P2, P1 is greater than P2, then what do you call it?
So lagging.
Sir, leading. Sir, leading.
Leading, yes.
Like
Yes,
Theta is
leading
less than
it.
0, so it is the capacitive load. Theta is less than 0.
Leading.
Okay,
Yes,
so
sir,
it is
leading circuit.
okay, so it is the leading load, that is the capacitive load. Similarly, if your P2 is greater than P1,
Theta is greater than 0.
Then it will be lagging.
inductive load.
Inductive.
Okay. So this formula is actually very important. If this tan theta equal to root 3 P2 minus P1 by P1 plus P2, there will be a lot of problems in the books using this power 3-phase power measurement by the 2 wattmeter method. Very important method. Obviously balanced load. So you have to correctly remember this formula, and okay, obviously this formula again depends upon depends on what? Can anybody tell? Huh?
Reference.
Balance.
Reference. No, balance. Okay. Who told reference? Who told reference? Huh?
Rajdeep Maji.
Rajdeep Maji. So yes. See, you see, I have done a very specific arrangement. I have connected 1 wattmeter in the A phase, current coil of the 120 in the A phase, the current coil of the in the C phase, and voltage coils in the B phase. Obviously, I am assuming A, B, C is the phase sequence, and then this derivation comes. If I do some changes, okay, you can see it in the books also. There are numericals. If I put this second wattmeter in the B phase and consider all the reference in the C phase, then there will be something different. Okay. So you have to read in sometimes some question it is told that a different arrangement is given and you are asked to calculate. So for the A, B, C phase sequence, if the first wattmeter is in the A phase, but the second wattmeter current coil is in the C phase and the reference is with respect to B, then this formula is valid. So for a given numerical, if you have to read the description and
I can't hear. Sir,
give your judgment.
sir, background noise is coming. Sir, background noise is coming, sir.
I know, but should I mute all of you? I can do that.
No, sir.
So this formula is important, but if you need to understand the derivation, and if you are given it, sum, just see what is given and how that formula, that sum is with respect to this derivation. There may be small changes. for which all these angles will change, and it may give give a different answer. So everything is with respect to this phasor diagram. So if I do some change in the phasor diagram, it will be a different situation. If I just change the phase sequence, or if I just change the second wattmeter, put it in the other phase and take the C phase as the reference, it will be a different situation. Okay. So now I give a small it is 5 or what? So I just give one small numerical, it can be done by, So there is basically a 3-phase motor, which is just a 3-phase load, which is developing 20 kilowatt at an efficiency. So this is a very common thing in industry, the motors connecting when operating at a certain frequency. It is developing 20 kilowatt. That means the output of the motor is 20 kilowatt at an efficiency of this. So what happens in a motor? In a motor, you apply electrical power, and it gets generated into mechanical power. Do you get the entire electrical power at the output of the motor?
No, sir. It depends on the efficiency.
No, sir.
No, sir.
There will be some losses. Okay, so there is a question of efficiency there. So what is actually given is the output power of the motor. So you can find out what is the electrical input. So what you can find out the electrical, see, if the output power is given, you can find out the electrical input. See, and in a motor, in a 3-phase motor, there is basically the coils are there, so the power factor is also given. So the question is, calculate the line current, phase current if the windings are delta connected. Okay. So you take this sum as your homework, you note it down and you do it, simple sum. So what you have to do is you have to do the electrical calculation. So the electrical voltage, line to line voltage is given 400 volts. The electrical input power will be what? Output by input equal to efficiency. Output 20 upon the efficiency will give you the input power. So you get the input power, you have the voltage, you have the power factor, you can find the line current. And this is the
output power is in?
Hello. I'm in a class. What happened?
Sir, output power of what?
Huh?
Output power of what? Of the 3-phase motor.
Suppose to this motor some fan is connected. Okay. This fan is connected. So that output power 20 kilowatt is obtained from the fan.
Okay, sir.
Sir, by supply voltage, do you mean line voltage or like VAN or VBN?
Here, what is given is line voltage. VL I have given.
Okay. We'll consider always line voltage if it's written supply.
It is line voltage unless something else is mentioned. Okay.
Okay.
Here it is given the supply.
Sir, what is the use of efficiency in this question?
Do you have any? Do you have any? Every one of us has some efficiency, isn't it?
Yes, sir.
Something input is. Are you 100% efficient?
So I'm 0%.
No, sir.
So there is a question of efficiency. So this is a motor. You are giving electrical power, you are getting mechanical power. So there is a question of efficiency. So I am giving you the output power. Using the efficiency, you can find out the input power. Voltage is given, power factor is given, you can find out the line current. Delta connected, you can find out the phase current. Okay, simple sum.
What is the answer?
Answer. Okay, then I have to show everything. Okay, the derivation is there. Okay, and again another thing is this is 3-phase. So this is the formula root 3 VLIL cos phi.
So how will we know whether it's leading or lagging?
It is motor. Okay, motor is full of windings. It is only lagging.
Yes, sir. Inductor.
It is not told here, but it is okay. So these are the answers. Okay, so we will stop here today.
Yes, sir, got this answer.
So we will have the quiz on this Saturday, and the homework
Sir, the results
the next Saturday.
Can
Thank
you
you.
take some problem sheet to practice?
Result of the previous
What results?